Welcome to the NHERI SimCenter's live expert tips. Today's session, we're joined by Dr. Song-Ri Yi, who is a postdoctoral researcher and part of the SimCenter software development team. Her background is in probability-based sensitivity analysis, surrogate modeling, structural reliability analysis, and random vibration analysis. And the title of her presentation today is Global Sensitivity Analysis on a Structural System. Thank you, Song-Ri, for being here, and we invite you to begin.
Thank you, Matt. Hello, everyone. I'm Song-Ri, and today I will talk about what is global sensitivity analysis and how we can run through quoFEM. Before we start, I will briefly review what is quoFEM. The full name of the tool is Quantified Uncertainty with Optimization for Finite Element Method. So we link a finite element model that you provide and uncertainty quantification algorithm we support. So what we basically aim for is that you bring the FEM model and we will take care of the rest of the UQ and optimization analysis. But in case if you want to go into more detail for these algorithms, you can always try to build your own quoFEM. We are open source projects, so we have everything on GitHub and we have nice documentation and we are always here to help you. And another thing you can do is to submit a feature request through SimCenter forum if you think it is like this new feature can benefit the many other users. Saying that, I will move on to what is global sensitivity analysis and why it can be useful in research. So to understand what is global sensitivity analysis, we will start with a numerical model. For example, if you have a trust model like this, and you will have a lot of random variables, like including geometric variables, material variables, and also maybe external forces. And then if you have more complicated model, then you will have more number of parameters. And you will start to wonder, like, will all of these input parameters actually contribute to the response? Or like which input factors are more influential than others? The method that can answer this question is global sensitivity analysis. So global sensitivity analysis basically aims to identify dominant parameters that controls a system of interest, and it can be used in many applications. As one fundamental application, you can use it to gain insight on your system. For example, if you have a nice model that demonstrates that simulate the propagation of ground motion through structure and assess the seismic risk, then there will be a lot of parameters that is associated in each steps. And maybe you want to identify like how the parameters and even their interactions affect the system. And then there will be some parameters that really does not contribute to the response of the model. Then in that case, it naturally leads to dimensionality reduction. So if you detect uninfluential factors or maybe redundant factors, you may want to exclude this or set this as some nominal deterministic value for the future analysis because it really does not affect the response. And also it can be used for informed decision making. For example, when you have a budget to conduct more measurements, then you will want to measure something that will reduce the response variance significantly. And finding these important parameters to measure can be also identified by GSA. And also when you do design optimization, you can identify most effective decision options among alternative by finding the one that have highest sensitivity index. That's one more possibility. And more importantly, it can be used for model diagnostics. So when you develop a model, it is likely that you may want to run like sensitivity analysis and compare the result with your intuition to make sure that your model is working properly. These days, sensitivity analysis is considered a requirement for good modeling practice. So now I will talk about what is sensitivity analysis. In particular, what is variance-based sensitivity analysis? Here I want to exclude most of the equations. There are a lot of equations you can find. So I will just approach in very intuitive and graphical way. So we start with kind of thought experiment. So consider you have a model that has input and output. First, consider that you generate a set of random variables from these parameters, and then you can collect corresponding output samples of the system. And then now you can draw scatter plots of its output parameters versus each output parameter versus output. For example, maybe you can first consider variable A and draw a scatter plot of A versus maybe mid-span displacement. And you will have some scatter plot like this. And in the second case, you can do the same for the other variable. For example, you can collect samples of E and draw it with corresponding output values. Based on this, we can have some intuition on how each variable affects the output. For example, in the first case, we can see that even though xi value changes, like mean of y does not really change much. It's almost constant. And that implies that xi is not really affecting the y values. On the other hand, and that means xi is likely to have low sensitivity index. And in the other case, you can observe a clear trend that as xj value increases, y is kind of decreasing. There are still variabilities which comes from other variables, but still you can expect that y value will change as xj changes. And that means xj gives some influence to the output and that lead to high sensitivity index. So here we can see that trend of y, like variability of the trend of y along xi is kind of the measure of sensitivity of each random variables. And that is exactly what Solver index is aiming for. So in this equation, this is the definition of sensitivity index. And this inside term, mean of y given xi represents this line of trend of y given xi, and variance operation represent how variable that line is. And then, so now we understood what is sensitivity index. So we will talk about how we can get sensitivity index value estimates. So as you can see in this definition, Solver indices involves both mean operation and variance operation, and that means it's like two-loop integration process. And you have to repeat this for all different random variables. So it's actually three-loop process, which takes long time even for very simple problems. So there are more efficient methods, and we have implemented those inside quoFEM. So among those methods we support, there is global sensitivity analysis. And here we have two different algorithms, which is from through SimCenter UQ and Dakota Engine respectively. So I will also briefly go over how its method identifies the sensitivity index without equations. So for the first one, it first generates the Monte Carlo simulation result of our model, as we discussed in the previous slides. And then we will get the samples, like the scatter plots as we saw previously. And then what they do is to fit these samples into a parametric model. But instead of using like conventional regression model, we use probability density function model. So this contour represents the density of each sample. So when they are dense, the contour, the function value is high, because that's probability density function. And for the parametric model, we used Gaussian mixture model. And the details of this method can be found in this paper. But the important thing is that since we have fitted this shape of data in a parametric way, we can easily identify the mean trend using this model. And once this trend is identified, estimating variance of this trend is also very trivial. So once the model is acquired, the solver indices can be acquired from the model. And this method, one benefit of this method is that sensitivity index can be directly obtained from Monte Carlo samples like blue points here. And that is good because if you are anyways gonna run sensitivity analysis, Monte Carlo simulations, then you don't need to run any additional simulation, but you can get sensitivity index as byproduct of your Monte Carlo simulation. So that can be beneficial when your computational model is expensive to run. But one thing to take caution is that since we have parametric model, it can be, so when data shape is highly irregular, it might not like approximate the data shape properly. So in such cases, you might want to use the other algorithm supported in quoFEM, which we call smart Monte Carlo approach. This approach is purely parametric one, but instead of doing the crude Monte Carlo simulations, it carefully selects the sampling point such that it can, it is easy to estimate the sensitivity indices. So instead of running just Monte Carlo simulation, it first runs generate a few Monte Carlo samples, and then it performs something like something called resampling. So given first set of samples, it wants to generate another sample set that shares the same xi value. So this is for the case we are interested in the sensitivity index of xi, such that so xi, they share the same xi values, but all the other random variables, or for the other input parameters, they have different values. So this discrepancy represents the variability from other parameters, like other than xi. And if you are interested in another sensitivity of another random variable, then you can do the same thing, but instead of fixing xi, these two sample sets should share the same xj values. And after identifying these two sample sets, then we can do some post-processing calculations to estimate the solver indices easily. For example, you can directly compare the correlation between initial sample set and the resampled sample sets. Then, for example, in the case one, they will not show much correlation, which indicates that there's no trend. But in the second case, they will have this red and yellow sets will have some correlation. And that indicates that there are some trends that between xj and y value. And actually, this correlation between initial sample and resampling set is exact definition, correspond to exact definition of solver index. So they are like equivalent. So in this way, the smart Monte Carlo gains some efficiency compared to direct Monte Carlo estimation. And also it does not introduce any approximation. So it's a symptotically correct, which is very powerful benefit of this method. But one thing to consider is that we cannot just reuse Monte Carlo simulation samples available. So we have to run separate analysis just for sensitivity analysis. So if your computation, if your model is too expensive, then you might not want to do this. And also, since we need to do this resampling process for each different parameter separately, the number of required number of simulations directly depend on the input dimension. So complexity is n times like number of initial samples times the dimension plus 2, but it is still much more efficient than pure Monte Carlo simulation. So there was the brief theory of sensitivity analysis. So I will move on to demo using quoFEM. So in this problem, we considered a simple, typical OpenSys model, like shear building OpenSys model with 7 degrees of freedom and 6 stories. And we introduced this material, nonlinear material model. And we are interested in 6 random variables. W is the weight of each floor, WR is roof weight, K, Fy, and alpha is characterizes the nonlinearity of our material model. And there's one more parameter that describes the scaling of ground motions. And for the excitation, we consider 2 different ground motions, Rinaldi and El Centro time history, which represent near field and far field ground motions. So I will show you how this sensitivity analysis for this model can be done in quoFEM. So for that, we start with our OpenSys model. So this is just ordinary OpenSys model that was not yet modified for quoFEM. So in the OpenSys, you set the variable using set command, and there are some commands to set the node and material properties, and there are scripts to run analysis. So first to show that this model is just ordinary OpenSys model, I will first run it through PowerShell. Although there are some warning messages, it runs fine, and we have some outputs that is expected from the OpenSys, which were set by recorders. But anyways, it is important to check that your model is working before fitting into the quoFEM. And make this script interface with quoFEM, you have to consider two things. First is input and first is output. So first, you have to let quoFEM know what is random variables among all the variables you have. For that, we have a command called pset. We can use pset instead of set, and then quoFEM will detect this command and use it as random, consider it as random variables. And that is all for the input part. And for the output part, we also have a rule that all the output quantities should be written in a text file called results.out. So this is an example of result.out. For example, if you are interested in 4 responses, it's just an array of 4 quantities respectively. So if your main model can reproduce this result.out directly, for example, you can set your output file of your recorder to be result.out instead of other names, then that's totally fine. But here I'm just showing you that we can also use post-process script to write result.out, and maybe you can use it for different applications. So sometimes it is useful to write this script, but it's totally fine if your main script already produces result.out, then you don't need any post-processing script. So once these input and output conditions are matched, you are ready to run quoFEM analysis. So I will just copy this address. And in SimCenter, I have recent quoFEM application. So we frequently update our tools. So it will be nice if you check our tools, whether the updated version is there. And so this is how our tool look like. So here we will run sensitivity analysis using SimCenter UQ engine, which is the parametric approach. We select sensitivity analysis, and for the sample, because it's live demo, I will just use like 15 samples, which is not close to enough. And for the OpenSys model, we will use the one we prepared. I copied the address, and the main input file was this file, and then we needed post-process script because this part writes the result.out file. And once you do that, you'll see that quoFEM detects all the pset commands, and it has already populated those variables as random variables. And the mean was also read from our OpenSys script, and they impose 0.1 of coefficient of variation. So I'll just keep it this way. And then for the quantity of interest, I want to check 4 quantities of interest, which are displacement at the first node, like peak displacement at the first node, and then peak acceleration at the first floor response, and then the 7th node is roof. 7th node corresponds to roof, so it's roof displacement and roof acceleration. So the 2 parameters here represent whole structure response, while the first 2 is only the first floor response. So if you did like that, and if you run the analysis, then it will give you the results. But since we used only few samples, it's not close to enough. So instead, and you can save the result using this panel, and also you can open the previous result. So I already saved some results here. So this is the Vinardo earthquake case with 500 samples. Here, first thing you can notice is that throughout 4 quantities of interest, actually WR, the roof weight, was not really contributing much to the response. And also alpha was not really contributing. So if you need to reduce the dimension of this problem, then I would choose these 2 values to be some deterministic nominal value instead of keeping them as random variables. And then one more thing to notice is that in the first floor response for the acceleration, the Fy was like yield strength was kind of contributing to the response. And that means we are experiencing some nonlinearities here. But if we go to whole building response, it was not really affecting much. So in this case, the stiffness or even it's obvious, but factor of ground motion was more critical in this case. And now we move on to the results from the El Centro earthquake. Here we first see that in this case, the factor of ground motion was affecting much more. And it was interesting to see that in this case, Fy was not really affecting to the response of the first floor response. And that may imply that we are not going through like high nonlinearity in this case. But one interesting thing I found was that in this case, actually Fy was pretty significantly affecting the whole structural response. And I thought this was kind of opposite from the previous observation of Rinaldi earthquake. So I thought it was kind of counterintuitive at the first time. So I decided to look into more details of this structural model and see what's happening inside. So one more thing is that if you go to documents, there will be a folder called quoFEM, and there's local working directory. And inside that, you have all the sample simulation results saved here. So each working directory corresponds to each samples generated by quoFEM. And all the OpenSys results are stored here. So I could use these files to draw this hysteresis curve. And this is like randomly selected 3 response of that. And for the first case of Rinaldi earthquake, as we had expected, we see kind of big hysteresis loop. And probably it's because of this pulse-like stroke shown in this accelerogram. And then as it gets higher, the response becomes mostly linear. On the other hand, if we see El Centro response, as we had expected, the nonlinearity behavior was not very big in this case. And that explains why the sensitivity index of Fy was not significant for the first floor. And then one interesting thought I had was that it's because this response actually ranges through covers both linear range and non-linear range. So that difference is not really highlighted in when we only see the first floor response. But when we see the whole building response, this rapid variability is kind of amplified through the building. and probably it appears as the whole building response. So I hope that could explain the observation we see here. And then there is something called groups over indices. So we can group our parameters with their properties. For example, this W and WR are both nodal parameters. And then these three are more like element parameters. And then we have ground motion characteristics. And sometimes we want to compare these parameters as a group. So when we run this, so in quoFEM, if you choose SimCenter UQ engine, it does allow you to set the groups. And after that, you see this group-wise over indices. And maybe conclusion that can be drawn from here can be like element model properties are as significant when it is combined. It's as significant as the ground motion factor. Oh, and here in this result, we are showing both main solver indices and total solver indices. In this presentation, I omitted explaining what is total solver indices. So it's main sensitivity index plus some interaction effects. So total sensitivity analysis additionally accounts for its combined effect with other random variables. So the value of total index is in theory always greater than the main index value. And because of some numerical errors, it can be smaller. The smaller total index is shown in this case, but theoretically it's greater than main effect. And remaining is just comparison with this of algorithms. And here with 1,000 samples, we can see both algorithm kind of are well converged and their results correspond to each other. And we see similar observation for other earthquakes as well. And this shows you the performance of each algorithm, how the model is converges as number of simulation increases. So in this case, I would say probability-based algorithm converges pretty faster because after 500 simulations, it kind of already identified these solver index values. But this smart Monte Carlo algorithm requires more iterations to identify the nice solver index values. So this almost concludes my presentation today. After this, so following is upcoming features of quoFEM. First, we want to implement GSA algorithm for high dimensional output, for example, like field outputs, so that we can have a nice field of sensitivity index values. And then other than that, we are also working on multi-fidelity surrogate modeling with adaptive design of experiment algorithms and also model selection and averaging based on Bayesian estimation theories. And then also we are open to the suggestions from users. Please, if you have some ideas for our next features, please go to SimCenter forum and let us know like what would be your ideas. And if you have questions and if you find some bugs, we are always happy to hear about it. And our policy these days is to monitor for forum every day, so you will get response pretty quickly. So we encourage you to visit our forum when you want to communicate with us. So I guess that's the end of my presentation. I would be happy to get any questions.
Yeah, thank you, Song-Ri. And at this point, we're going to save questions for the unrecorded Q&A session. One of the incentives for joining us in person is you get to ask questions to the presenter. But thank you for sharing these other live expert tips that are coming up. In the next, I guess it's a month or so, we have additional a presentation by Dr. Akash Bangalore Satish, also focusing on the use of quoFEM. That's December 10th. And we have two presentations that introduce the Hydro UQ tool, which is going to be presented by Dr. AJ Harish. And we also have a live expert tip coming up with Dr. Stephen Gavrilovich, which is going to use the Regional Resilience Determination tool. So you can register for each of those events on our webpage, simcenter.designsafe-ci.org. And we look forward to having you join us for those events in the near future. Song-Ri, thank you very much for the presentation, and going over the example is really informative. Thank you very much.